Hey class, it's me again doing 3.1. We're doing 3.1 to 3.3 because they're pretty connected, and 3.1 is Extrema. And I have here let f be defined on the interval I containing c. F of c is the minimum of f if f of c is less than every f of x on the whole interval. This is like a lot of jargon for you. F of c is the maximum if f of c is greater than any f of x on the interval. That's all that's saying. Here is how it looks. Everybody has stopped in the library and is now looking at me, okay, and they're laughing. So anyway, here's what we got going on. Here's a min, here's a max. Fantastic. Open interval doesn't include the endpoints. There's only a min, no max. Oh, closed interval, here's here and here, no min. So not every function has a min, not every function has a max. It depends on whether it's open, closed, how it looks, holes, no holes. You with me? Are you with me?
Yeah.
Okay, she's with me. Then we have the extreme value theorem. That sounds exciting. All right, you probably get a date saying that to somebody. Extreme value theorem? Sure. All right, let's go. If f is continuous on a closed interval, then f has both min and max. So continuous, yes, yes. Max and min, you have it. And here it is. This is what it looks like graphically. Hills and valleys. You learned about that. I know you learned about that. So there's your max and mins. Critical number. Ooh. Critical number is when you set the derivative equal to 0. Then if the c is a critical number. That's all this says. You could pause and look at it for about 3 hours, but that's all it says. Your guidelines. So, more like Kennedy, I'm talking to you. Okay, you like this. All right? Find critical numbers. Evaluate at each critical number. Evaluate at each endpoint. The least is the minimum. The greatest is the max. Done. Okay? Those are the rules you go over all the time. Now, these critical numbers are when it equals 0 or undefined. All right? Here we go. We got more. Well, let me double check back. That was it? Okay, we got more here. Here we go. Look at this derivative. Decreasing function, constant, increasing. Check out derivatives. Derivatives here is decreasing because if you look at a line, take a look at this line, see? All these are decreasing. It was very, very, very a negative slope, very steep to almost to 0. So it's decreasing. This is constant, and these slopes are increasing. Nice, nice? Okay. I'm getting a nod that it was nice, nice. All right. Now you test for this. How do we test for this? If the derivative is greater than 0 for all x in the interval, then it's increasing. If it's less than 0, then it's decreasing, and it's constant. There it is in math terms. All right, here it was visually, math terms, nice, nice. Relative maxes and mins, here we go. What we're going to do is we're going to use a sign analysis. We're going to take the critical number, we're going to check left and right of the critical number. And if there's a change, like goes from negative to positive, look, I could draw a thing that goes from negative to positive. Watch, 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 watch. Negative, positive. Look at the slopes. I have a relative min. Okay? And if it goes from positive to negative, I have a max. All right? So that's what I'm looking at. Likewise here, if I go from positive to positive, it's neither. Negative, negative, neither. So that can happen too, and it does. All right. Now that all that mambo jumbo's gone, let's show you how to do it. This is going to be easy. Even Alyssa would be able to do this. All right? So it says, find the critical numbers, open intervals of increasing, decreasing, locate all relative extrema. I need water. First thing we do, take derivative. You guys are derivative experts. You know this. Nice, nice. There it is. They set it equal to 0. So I can set this baby equal to 0. I'm doing this without my notes, as Alyssa knows. So I'm a little nervous. Factor out of 2. And I noticed that we got a critical number. The critical number is x equals, oh, I don't like the way that looks. Come back, nice. Nice. X equals 3 is a critical number, Cn. Okay? So now we're going to test that critical number. We put 3 here, and now we're going to look. Fine. All right, now what we're going to do here is we're going to test to the left of 3 and to the right of 3, and we test inside the derivative. So pick a number less than 3.
5.
5. 5 is not less than 3. Okay, that was a calc student, by the way. 5 is greater than 3. So we're going to check 5, which is greater than 3. Let's plug in 5. 10 minus 6 is positive. Now we're going to pick a number that's less than 3.
2.
2. All right? I probably would pick 0 because when we plug in 0, it's easier to check it out. But if you plug in 2, you get negative 2. If you plug in 0, you get negative 6. So it goes from negative to positive. We just learned from the other slide, okay, that going from negative to positive is a minimum. All right? So let's write this. AP does not allow you to do this. You can do this for yourself and for my class, but what you're going to need to do, they don't allow the sign analysis. I don't know how to spell analysis, but that's it. Okay, I got it. They don't take it as a form of proof. So this is what we have to write. Okay? It asked me, find critical numbers. So we found a critical number. Number is x equals 3. Okay, found a critical number. Now, f of x is decreasing on negative infinity to 3 because it was minus. And I have to say because f prime of x is less than 0. So that's what you have to write everything I'm writing. Okay? F of x is increasing on 3 to infinity because f prime of x is greater than 0. That's what you have to write. Okay? And locate all relative extrema. Well, this means since the derivative changes from positive or decreasing to increasing, at 3, x equals 3, x equals 3, or get the point, 3 comma, remember, plug it into the original. 9 minus 18 is negative 9, is a relative, let's see, decreasing to increasing is a relative what? Decreasing to increasing? That looks like a relative min. That's it. So this is what you would have to write for the AP and my class. And that all comes from this little sign thing. Nice, nice. You know, sometimes big things come in little packages like this one. All right. I have another problem for you to gander at. So we're going to gander at it. I'm going to talk you through it. It's done already. In the interest of time, I did it. So we take the derivative. Power rule. Hooray. And now we factor. Nice, nice. And we set it equal to 0. So we have 2 critical numbers now. Now we have a critical number of 0 and 1. Here's 0. Here, I'll highlight. Nice, nice. I like using this highlighter a lot. 0 and 1. So now we're going to check the derivative on both. So we pick a number that's less than 0, like some negative number, like negative 1 or negative 1,000,000. Okay, you pick. Pick a number between 0 and 1. Now there's not that many, right? There's infinite amount. You should know that. All right, well, I'll pick a half because I know what to do with a half. And then I'll pick something positive. I'm sorry, I'll pick something greater than 1, like 1,000,000, see if it's positive or negative. We're only checking the sign. We're not really concerned about what the answer is. We're just doing the sign. And you can see, when I checked it, this is what I got. So, what does that mean? That means from negative infinity to 0, I'm still on the thing, which I don't want to be. Negative infinity to 0, it's increasing. There's the plus. From 0 to 1, it is decreasing. There it is. and from, I don't know why that's negative 1/2. Oh, I guess that's what I checked. All right, and then from 1 to infinity, it's increasing. These points plug into the original equation to get these points. So that's what I did. I plugged into this original equation, got 0, 0, and 1 comma 1/2. So now we can say a lot about them. You say, because there's a change from increasing and decreasing at 0, 0, increasing and decreasing, that's a relative max. Nice. Because there's a change from negative to positive, okay, right there, that's going to be a relative min. And I could also say that this is increasing, decreasing, and increasing due to its derivatives. Got it. You try. This is a U. I say find everything. Critical number, a relative extrema, la la la. You got it? Okay, you try that. Next. Try that one. Yes, yes. We have to do a little product rule here. You want me to start it? Yeah. You know what? Alyssa's going to start it. Here she comes.
Oh, dear.
Here she comes.
Hi, friends.
You can say, looking at. Looking.
So sine would be cosine x. What am I doing? Product rule?
Yes.
Okay. Fishing great.
Yeah, I would do sine then.
Then, so negative sine x.
No, you're getting crazy.
No,
Yeah, you are. Erase it.
I'm sorry.
It's okay.
Can't work under pressure.
A lot of pressure here at the camera and stuff. All right,
This is
erase
so
the other one
embarrassing.
too. Don't be embarrassed. Okay. First derivative, second.
Sine x. Negative sine x.
Mm-hmm.
Plus
Second derivative first.
negative
Second. Just put cosine.
cosine x.
Cosine.
Cosine x.
All right. Make it nice. Negative sine squared x. Equals 0. Perfect. I'll take over from here. All right, I'll take over from there. Tag in, tag out. All right, we got them equal to 0. Now, when do they equal 0? At 0 comma 2 pi. So we're kind of looking when the sine is 1 and the cosine is 1. All right? I'm leaving that up to you. All right? I think when you add them up, like square root of 2 over 2, square root of 2 over 2 might be something that we look at. I don't know. I really don't know the answer, but I'll know by the time you watch this. All right? Just a hint down here. Look at the quarters. Okay? This is the graph of one of these sine, cosine x maybe. This is maybe the sine, cosine x. Look at the graph. Look where it has the relatives, mins, and maxes. See if you get that up above. All right, so you got two problems to do. You got this problem from back there, the x plus 1 over x, and then you have this one to play with. You have any questions? If I'm sure I'll hear them tomorrow. Enjoy. Thanks for watching. At Frank Marascio. I'm sorry, at F Marascio.